Welcome back, class. Tonight we're going to discuss kinetic energy in collisions. And recall there are two different types of collisions. There are elastic collisions involving two objects that are bouncing apart. And then there are inelastic collisions involving two objects that stick together. Those of you in first period, we've already discussed this about a week and a half ago, so this is not new, but will be a good review for you. And my second period students, this would be a good review based on what we learned today. So let's go ahead and look at an example. A 10,000 kilogram runaway freight car traveling 7 meters per second collides and couples with three 10,000 kilogram freight cars moving 1 meter per second in the opposite direction. Is kinetic energy conserved? If not, what is the change in kinetic energy? So first we have to know how to find the velocity of the freight cars after they collide. So do you remember how to calculate the velocity after a collision? Of course you do. It involves the use of conservation of momentum. So let's go ahead and write down our MVP chart and fill in the information. And you can go ahead and pause this to fill in the information. And that way I don't have to pause, and you can just do that whenever you need to. So here are our initial data. 10,000 kilograms is the car that's run away, moving 7 meters per second. And then we have three 10,000 kilogram freight cars traveling 1 meter per second in the opposite direction. So here's our 30,000 total mass moving in the opposite direction. Remember, if you're moving in the opposite direction, your velocity should be negative. All right? And then here, after the collision, we're going to be all stuck together, a total mass of 40,000. So let's calculate our momentum before. 10,000 kilograms times 7 meters per second gives us a momentum of 70,000 kilogram meters per second. And for our three freight cars traveling 1 meter per second in the opposite direction, we get 30,000 times -1, or negative 30,000 kilogram meters per second of momentum. And we're going to add these together. Remember, 70,000 plus a negative 30,000 is like subtraction. So we get a total momentum of, that's correct, 40,000 kilogram meters per second of momentum. So what's our momentum after the collision? Is it going to be larger or smaller or the same? Yes, it's going to be the same. Momentum is conserved in all types of collisions and explosions. So now we've done all the hard work. Now we have 40,000 kilograms of mass times what velocity would give us 40,000 kilogram meter per second of momentum. And of course, you don't even need to do the algebra here. The answer is obvious. It's 1.0 meters per second. Now, let's talk about kinetic energy. Let's make two more rows. One that shows kinetic energy. Remember, we calculate kinetic energy as 1/2 mv squared. It's measured in joules. So let's calculate the kinetic energy of the 10,000 kilogram car before. So we need to do the math. You may need a calculator, so you might want to pause if you need to get a calculator. So first we're going to square the velocity. 7 squared is 49. 49 times the mass, which is 10,000, gives us 490,000. And half of 490,000 gives us 245,000. We'll see that in a moment. And then, of course, we're going to calculate the kinetic energy of the 30,000 kilogram, three freight cars at 10,000 kilograms each. Negative 1 squared is simply 1. A negative times a negative is a positive. 1 times 30,000 is 30,000, and half of 30,000 is 15,000. And remember, kinetic energy is not a vector quantity, so we're going to add these two together and get a total kinetic energy of 260,000 joules. Over here, our final velocity, 1 meter per second. Square that, we get 1. Times 40,000, we get 40,000. And then half of that gives us our 20,000 joules of kinetic energy afterwards. So what is the difference in kinetic energy before to after? What is our change in kinetic energy? That's right, our kinetic energy decreased 240,000 joules in this inelastic collision. And that would be why, if you could imagine this scenario, that would be why these freight cars would crash and they would crunch together and jumble into a big mess of steel. It's a very dangerous collision. If there were people on board a train and this were to happen, it could be very, very damaging and deadly. So a lot of energy is going into mangling and bending and increasing the temperature of that metal through that process. It's a lot of energy to be lost. So let's go ahead and do this sentence frame right here. While blank is always conserved, blank energy is only conserved in blank collisions. Blank energy decreases or increases in inelastic collisions. This energy ends up in the atmosphere as blank energy. So let's go ahead and fill these in. While momentum is always conserved, kinetic energy is only conserved in inelastic collisions. Kinetic energy decreases in inelastic collisions. This energy ends up in the atmosphere as thermal energy, and that's the energy of heat. So I hope this helps you understand kinetic energy in inelastic collisions. Elastic collisions, both kinetic energy and momentum are conserved. There's no work being done in elastic collisions. There's no mangling and crunching up of the metal where a force times the distance is applied. It's just bouncing off. So energy is conserved in energy is conserved in elastic collisions, kinetic energy that is, but it is not conserved in inelastic collisions. See you tomorrow.